Welcome back to Forge College. In our previous lesson, we looked at how to find and use API references to talk to the blockchain. Now we're exploring the actual consequences for developers when they choose the Ethereum account model over the UTXO model. Take a look at this document being swarmed by cursors. To understand the Ethereum account model, imagine editing a single shared digital document simultaneously with a million strangers. Everyone is trying to rewrite the same lines at once. We previously saw how the UTXO model works like handing someone discrete physical dollar bills. Ethereum is different. It doesn't pass bills around. It literally erases your old balance and writes a brand new number directly in its place. This approach saves a lot of digital space because the network only has to track one current number for your account rather than a growing pile of individual bills. However, this efficiency creates a bottleneck. Every piece of code you write is now fighting to edit that same single source of truth at the exact same time. Because Ethereum updates everything in one place, developers have to change their entire strategy. Writing smart contracts, designing user wallets, and even hunting for bugs requires a specific set of rules to keep the data from turning into a chaotic mess. Ethereum uses a nonce, a strict delay counter ticket system. You can't edit until your number is called. This forces wallets to manage a pending state. If ticket 4 for a coffee is stuck, ticket 5 for a digital cat must wait its turn. A good wallet manages these expectations. It doesn't just show your current balance. It tracks that chronological waiting line so you don't accidentally try to spend money that is already reserved for a transaction still in progress. For smart contract developers, the in-place model means the old data is gone the second a transaction succeeds. There is no historical record left in the account itself, just the new result. This creates a security risk. If a developer writes floppy code, a bad actor could wait for the contract to ask another program for information and then sneak in to change a balance while the first operation is still unfinished. To stop this, developers use strict safety checks. They write code that looks at the document's state right before a handoff and verifies it again the moment the contract regains control, ensuring no sneaky edits happened in between. Under this model, contracts must be inherently defensive. Developers rely on their own internal bookkeeping to double-check the math, rather than assuming a user's balance hasn't changed during the middle of a transaction. If everyone edits one document, they can't work at once. We must split it into smaller clipboards. But strict deli tickets force a trade-off. Developers solve this by partitioning state, breaking the document into independent subaccounts, so parallel edits happen without traffic jams. Scaling an account-based network always involves this trade. You give up the simplicity of a single document in exchange for a more complex system where you have to coordinate many accounts at once. All this constant rewriting makes debugging a challenge. How do you find a bug when the evidence gets overwritten every few seconds? On this timeline, developers act as detectives. First, take a pre-state snapshot of balances. Next, run a step-by-step replay, showing every instruction like a slow-motion video. Finally, compare the before and after to find the exact moment the document changed in an unexpected way. Since mistakes in this model change the account state directly rather than creating a separate bad output, this chronological step-by-step tracing is the only way to prove a contract is truly safe. Building on Ethereum means treating transactions as ordered edits, designing wallets that manage traffic, and debugging in slow motion. In our next lesson, Transaction Basics and Structure, we'll finally look under the hood at the specific fields, like gas limits and data payloads, that make these ordered edits possible. This video was made by Forge College. To learn more about this and other Web3 topics, visit us at forge.college for more educational resources. See you next time.